Solve this problem is it's going to have 2 times as many unknowns as we have components in the system. But what we use to solve it are the equilibrium equations and the material balances in combination. So our way of solution is a bit different. The first thing we have to think about is, another comment is that the feed comes in, we don't care what the phase state is, or if it's a mixture of liquid gas or if it's all liquid or what it is, because we assume that right away it comes to the temperature and pressure of the flash unit. So all that we care about to characterize the feed stream is what its composition is. So the first thing we need to worry about is that we actually get a split. This is the idea. This can be done actually because we want to do a liquid, we want to do a fluid separation process, taking advantage, as usual, of the fact that the vapor composition is going to be different than that of the liquid. But we have to get a split, and for that we have to notice certain restrictions. Let me go over to a new page if I can. And we have to be in between, if we're, for a given, the pressure of the drum, we have to be in between the dew point temperature and the bubble point temperature. Or we look at it from the standpoint of the temperature of the drum, we have to be between the dew point and bubble point pressures. So let me make sketches of those. I think that would be best first, and then write down what the requirements are. Close enough. So if this is a case where T, let's see, that's the temperature of the flash. And here's my X1 and Y1. So this is my bubble point pressure, and here's my dew point pressure. And this is the pressure of the flash. The pressure has to be somewhere that I find myself with a system which is going to split into 2 phases. So let's just let this be Z. I'm assuming now I got a binary, so I can do that. Now, so if that's Z, the pressure is going to have to be somewhere between here and here. All right, so if I have a pressure between there, then here's the tie line, and I get a split. Here's my liquid, and here's my vapor phase compositions. So what that means is that the pressure of the flash here must be between the dew point pressure at Y1, oh geez, not enough room. Let me write it out and then talk about it. That's a way of stating what I've shown here graphically. That I have to have a flash drum pressure between these limits in order to get a split. Now if I had the diagram here in terms of the flash pressure, and that means what I've got here is temperature. Then it's going to look like this. And have a similar thing, X1, Y1 here, and let's let myself some more room there. And let's say we got Z1 here. That means that my temperatures have to lie in this region, so that if I have it between this region and I have a tie line, so I've got a split between the vapor and liquid as indicated there. So here the requirement is going to be, it takes a little more space to write this out, but let me just write it out. C1. So the first thing we want to just kind of assure ourselves that we're in the right range, so we're going to get a split. And if we do, then we can proceed towards solving the problem. And we solve the problem. The problem is the one that I stated over here. Given the feed composition and the temperature and pressure of the flash drum, we're asked to calculate how that splits, as how much of it ends up being vapor and how much of it ends up being liquid, and what the compositions of each of those phases are. And the way we solve that is to use material balances. Let me ask you, have you done this problem in 310? It's quite often a 310 type problem, so assuming it's not totally foreign to you. So our material balance is that we have overall, we have L plus V here is equal to 1. And for every component, let's say component I have the statement that Zi is going to be equal to XIL plus YI times the big capital V. And I'll eliminate right away capital L, so I can write this equation for each component is equal to Xi 1 minus capital V plus YI capital V. And then I have equilibrium equations. They're all going to be written using the K-factor notation. So I haven't said what kind of system I'm dealing with here, so presumably I could use any kind of system. Yeah.
The L and the V, do they stand for moles?
Liquid fraction.
Oh, liquid
the fraction that ends up being a liquid
okay.
phase. V is the fraction, so they're dimensionless fractions.
I
Sum
get
to
you.
1.
I get you.
Yeah. All right, so these K's are going to depend on the situation that I have. Now, the best situation of all would be Raoult's law, and that's the one that satisfies both of those simplifications that I talked about earlier. So this is the happy circumstance, and it's probably the one you did in 310. Then Ki is just equal to PIS over P. That's Raoult's law, but not otherwise. Otherwise, you saw what Ki could be when I discussed this whole K-factor method. So depending on the type of system you've got, then you have different circumstances. So modified Raoult's law, I can ran out of space in the bottom here, but then Ki would be equal to gamma I BIS over P. And if I had the method where Lewis and Randall rule holds in both cases, then the KIs would just be pulled out in terms of pure components with the KIs just gotten off the nomograph. So whatever the situation may be, then the calculational method for solving the problem would go something like this. So, all right, let me actually do it. So the first thing we do is to write down our equilibrium equations like this. And then we can express material balances this way. Z is equal to xi 1 minus r capital V plus yi times V. That's just, I'm just rewriting the material balance equation I had earlier. And now in terms of the K's, this becomes following. Or I could rearrange this equation to be explicit for each of the y's. Now, we don't have the composition in either of the phases, so we can work with whichever one we want. I've chosen to work here with a vapor phase composition, but I could have formulated in terms of the x's as well. But now we proceed towards solving the problem by requiring that the sum of these yi's equals 1. And if I write that out, that looks like this. I better use the same notation for my z's. So this is the equation to be solved for V. If for a binary, let's see if I got enough room. Becomes a little easier to see if we limit it to 2 components. The equation I need to solve is the following. So you recognize these, this is y1, this is y2. So I've just written them out. But this is the equation that we need to solve for V, and this means finding a root for it. So if we have, the K1s are just going to be constants, like they would be if we had validity of Raoult's law, then those constants could be plugged in, and we can solve this in a straightforward manner. If the K values are functions of and that would also be the case if I had the K factor method that I've described where the Lewis and Randall rule is valid for both phases. That would also be all done at this point. I would solve for V, and then I'd go back and solve for the Y's, and then I'd solve for the X's, and I'd be done. But if I've got gammas in there, using the modified Raoult's law, then I have to set up an iterative procedure to solve this. So I start out by assuming that all the activity coefficients are 1. I don't have time to go through this, so we'll finish this next week. But just to say how we would go, we start out by setting all the gammas equal to 1. That'll get us an initial set of x values eventually. That gets us a new set of gammas, and we do that over and over again until we finally converge. And that means in your spreadsheet it's a little bit difficult because one of the columns is going to require a root each time for this value of V. But it's been a little bit fast, but we'll finish this up and I'll show you an example where we actually have to do that iterative calculation then next week. And that's what is going to happen now. It's going to be a long time because we have President's Day coming up on Monday. So the next lecture will be Tuesday. And then we'll have Tuesday and Wednesday lectures, then we'll have a problem set. And then the following week is going to be midterm. So I'm actually done for today.